At the moment, T equals 0, a 26-volt battery is connected to a 5 millihenry coil and a 6 ohm resistor. Immediately after, how does the potential difference across the resistor compare to the EMF across the coil? Answer the same question about the circuit several seconds later. Is there an instant when these two voltages are equal in magnitude? And then when? And finally, a 3.4 amp current is established in the resistor and coil. The battery is suddenly replaced by a short circuit. Determine the voltage drops across the resistor immediately after and a few seconds later.
So this is the circuit. We got a 26-volt battery, a 5 millihenry inductor, and a 6 ohm resistor. And it's all connected at time t equals 0. That's just objectively when it starts. And part A is asking what is the respective voltage drops across both the inductor and the resistor. Okay? And it starts off with 26 volts, so we know that they're going to have to add up 26 volts, right? Because conservation of
energy.
Yep. Conservation of energy. Kirchhoff's loop rule.
Ooh.
Okay? And we know this is an inductor. So the charge wants to go like this, right? Right at the beginning. But this inductor is basically like, nah, you're not going anywhere. Because as the current starts to go that way, the inductor is going to start pushing it that way due to Faraday's law and all that magnetic good stuff. So actually, this is going to have 26 volts, and that's going to have, if that's 26, what's that have? Zero. That's kind of what the whole point of an inductor does. Well, resistor resists current, right? Because it's a resistor. An inductor resists changes in current, right? So the current, at time before it starts, there's zero current, right? And all of a sudden, it's like, let's try and jam current that way. This is basically just like, nah, go back the other way. So there's nothing there, okay? But then, this thing doesn't last forever. Eventually, a charge gets through, and the current flows. So after a few seconds, this is just treated as a normal wire because the magnetic flux is not changing because there's a constant amount of current. So if that's just a normal wire, it's going to have 0 volts. And then, if that's 0, what does that have?
26.
26. Okay.
Yep.
And part C asks if there's a time when the voltage drops across the inductor and the resistor are equal. Well, yeah, there kind of has to be. If that goes from 26 to 0, and that goes from 0 to 26, and energy must be conserved, there must be an intermediate point when they both have the same value. And if two things have equal value and add up to 16, what?
26.
If two things are equal in energy and add up to 26 volts, what's the value on each one?
13.
Yes. So it means they both have the same voltage when they both have 13 volts. So I could come up with some equation which involves the time derivative of current to solve for the EMF, the induced EMF, or I could just go to resistor because resistors are so much easier to deal with.
Mm-hmm.
And that's what part D asks us to find this exact time. So we know I is equal to E over R, or epsilon over R, which is also the original current, times 1 minus E to the negative T over tau, where tau is equal to L over R. Okay, so that's helpful, except we have to find out what current will give us 13 volts with a resistor of 6 ohms. So we're gonna go back a little bit. EMF is equal to IR. And now I want to solve to get the I by itself.
Divide R.
Yep. And what's the voltage?
13.
Yep. Resistance?
6 ohms.
What's 13 divided by 6?
2.167.
Yep. Okay, so we have to find out when the current is equal to that, because that is the time when that resistor has a voltage drop of 13 volts. So, we gotta go back up here.
Mhm.
So, 2.167 amps is equal to epsilon over R times 1 minus E. Plugging in for tau. Okay. And let's do some algebra before we plug in our numbers. So we got 2.167 amps times R over epsilon is equal to 1 minus E negative RT over L. We plug in our resistance of 6 ohms and our voltage value of, this is for the whole circuit now, so 26 volts. This actually is 0.5 is equal to 1 minus E negative RT over L. Subtract 1 by both sides. I get negative 0.5 is equal to negative E to all that. Multiply both sides by negative 1. 2.5 is equal to negative RT over L. And then we got to take the ln of both sides is equal to negative RT over L ln E. But everyone knows the natural log of E is just 1. So solve for T. We got ln of 0.5 times L over negative R is equal to T. Okay. Plug in your inductance of 5 millihenries and your resistance of 6 ohms, and you get a time of 0.5777 milliseconds. And then part E, we replace the battery. Battery's gone. Battery's gone.
Uh-oh.
Come over here. So instead of the battery, we just have the inductor and the resistor. And it says that the current is 3.4 amps. So immediately after the battery is miraculously taken out, because the current was originally going in this direction, the inductor is going to keep making it go in this direction with the same magnitude. So shortly after this happens, the voltage drop is just going to be equal to the current times the resistance, which is 3.4 amps times the 6 ohms, which is 20.4
volts.
And then, since this is a closed circuit and we're not adding any energy to it, as it keeps going around and around and around, the circuit keeps losing its energy at the resistor, either in the form of heat or light, depending on what kind of resistor it is. So as T approaches infinity, the voltage on the resistor approaches 0. And the challenges I originally faced were determining what these values were, because inductors are kind of complex, and the time terms WebAssign used were not very specific. A short time after could be 1 millisecond or 10 minutes. It was pretty vague. And how was I supposed to know that in 3 seconds the whole circuit was at a stable state? Like, it didn't give you enough information. And then this shows my growth as a physics student, because it shows that I understand RL circuits, which are the last type of circuit we will cover in this class. And I'm able to manipulate the current and EMF values to determine the voltage drops across inductors and resistors in a circuit at any given time. And this is coming at you live from the 32nd day of quarantine. And this is the last physics video, so we're all a little sad. The end. Yes?
It's Murphy's Law. Did you guys go over that?
Yes.
Was
That
it
one I-
fun?
Yes, that when something can go wrong, it always will.
Sweet.
Alright, this video's over. The end. The last video ever.
You're probably gonna have to make some in college.
Probably not. No one cares in college.